Good afternoon, everyone. I'm Balázs Teréki from AI Motive, and I would like to talk about the very interesting topic of optimal scheduling in a multi-GPU environment. You can see our program here for the next 20 or 30 minutes. I will briefly introduce you to the huge challenge of simulation for self-driving. I will also tell you a bit of history about our simulator. Then I will show you what we want to schedule by presenting our sensor system and rendering pipeline. And in the end, you will see how we managed to implement a scheduling system which enables us to have a real-time simulator using multiple GPUs. Let's get started with the introduction to our simulator. Every software development process in the end comes to testing. And as you might have heard about recent accidents on the road involving self-driving cars, you can say this field indeed needs lots of testing. Before going into production, self-driving cars have to drive huge distances in various road conditions and environments. But even if we had the sufficient resources, it would be impossible to test in every scenarios. So it would be really good if we had a set of tools which enables us 24/7 testing availability and the virtual environment in which we can do, and we could do anything without having the fear of the consequences. This is what a simulator is. Let's take a look at what specific demands a simulator has to meet. So we have to simulate diverse environments, road conditions, and driving cultures. You know, there are lots of crazy drivers and impossible scenarios on the road. We have to be able to repeat our tests and scenarios, and for that, pixel precise rendering and physical realism is crucial because differences between rendered images from previous runs can disturb, for example, the self-driving car's recognition module. We also provide ready access for self-driving developers and engineers, and we have to use efficiently our hardware resources because it is as important for a developer who wants to run a test on his laptop as running stability tests on servers. But let's talk about a bit of history first. So our first thought, our simulator could be a modified game engine. So the first iteration was based on a game engine. But during the development, we faced several problems. We had to simulate various types of camera lenses, like ultra-wide lenses and narrow camera lenses, and we had to modify the game engine's rendering pipeline, but our modifications didn't really fit, so it caused performance issues, and also artifacts occurred on post-process effects. And also, there was no support for using multiple GPUs. So in the end, we decided to make our own simulator from scratch, but we learned a lot during the development of our first simulator. Those specific demands were formulated during the development of our first simulator, and those experiences helped us greatly to design a sensor system and the rendering system, which I will present you on the next few slides. But first, I want to talk about our rendering pipeline. So in our simulator, synthesizing images means we have to simulate lens distortions, lens effects. We have a GPU rasterization pipeline for this problem with a bit of shader magic. And I would like to add that in the future, ray tracing might be a possible option, because with ray tracing, it's easier to simulate those distortions and lens effects. We use a Vulkan-based graphics backend because we had to support multiple platforms like Linux and Windows, and it enables us to use multiple GPUs for rendering. So we built a complex rendering pipeline with two big phases. Like the first phase is an environment capture. Basically, the rendering pipeline renders the scene into a standard 2D or a cube map target. And in the second phase, we sample that captured data to simulate lens distortion. You can see, I want to share some details about those two phases. So the first one is the environment capture. Firstly, we render the shadow map, our shadow maps, taking the field of view of the camera into consideration. Then in the deferred rendering pass, we generate some gbuffer information and also some data for ground truth testing for the self-driving software, like segmentation images, depth, distance images, and so on. And eventually, we do the shading. We also render an image-based or a calculated atmosphere, and in the end, in a forward rendering pass, we render the transparent objects and some foliage. After that, we have to distort the captured data. So we sample the captured environment with a specific algorithm based on what type of lens we are using. So for example, if we have a fisheye camera, then we render the environment into a cube map, and then we generate rays in a shader to sample that cube map. And as you do, in the end, we do some tone mapping and anti-aliasing. Now I would like to talk about our sensor system and the schedulers. Basically, our simulated world is a graph of virtual objects, hierarchy of various types of nodes, like actor nodes, scene capture nodes, mesh nodes, and so on. The basic concept is that you can build a scene with those nodes, and scene capture nodes can be attached to an actor, and after that, those capture nodes must provide data for their sensors. To make this robust system work, we have to manage our resources well. So we designed the system in a way that it can execute multiple tasks generated by the sensors simultaneously on CPU cores. And after that, if it comes to rendering, we can distribute our rendering tasks among multiple GPUs. So then we implemented a CPU and GPU scheduler for this purpose. I want to show you a typical sensor setup. So you can see here, imagine a vehicle with several lattice sensors. In our system, this will be a vehicle actor with scene capture nodes attached to it, and these nodes will provide data for those sensors. Now let's see how our sensor system, basically the CPU scheduler, works. So you can follow the capturing process on this slide. Those boxes are tasks in green. During the simulation, in every tick, we have to build this task graph for each and every sensor, and then execute those tasks. And these tasks in line can be executed simultaneously, and the arrows means dependency relations. There are three phases. The first one is an update phase. We update our capturing volumes, also known as frustums. I would like to add that not every sensor needs rendering. So maybe if we have radar, for example, the only task on this task will be executed and will be put in the task graph. So after the update phase, we have frustum calling. We collect all of the objects in the scene which are falling into that capturing volume, and if that's the case, we render them in the render images pass. And so that means we have to generate a GPU task for the GPU scheduler, and that's how we realize our rendering pipeline. And in the last phase, we process the captured data, and basically that's the sensor capture. So as you can see, this task graph basically defines our CPU scheduling, and this task graph will be given to our TBB-based CPU scheduler. Now I would like to talk about this GPU scheduler, which the GPU scheduling happens in the render images task. So we render lots of images like RGB, Bayer encoded images, segmentation and distance images, and so on. This task can be also broken down into two phases. Like we have to collect and execute our rendering operations, then do the rendering, and we have to read back the images from the device. The purpose of this is we can overlap these two phases and gain performance. We have the GPU scheduler. This scheduler manages our GPU resources and chooses a GPU and a GPU slot for a task. Before going into detail, I would like to clarify some definitions. So, a GPU slot is an operation buffer on a specific GPU. So you can put those operations into that. And the GPU task is a subset of GPU operations for a GPU slot. And the GPU task queue is a set of GPU tasks which will be submitted to the GPU. You can see our GPU scheduler architecture here. It has two main parts, the off-screen back buffer and a GPU resource container. The off-screen back buffer is responsible for managing our GPUs and GPU slots. Basically, an algorithm chooses the least loaded GPU based on the number of tasks, a number of free slots on that GPU, and it selects a free slot, and that slot will be given to the GPU task queue. We also, the GPU scheduler also manages resources. So when a participant asks for a resource container, all the sufficient resources will be allocated on all the devices in a resource set, like gbuffer textures and so on. So let's see how it works. During loading time, we have an initialization part for the scene capture node. When we instantiate a scene capture node, a GPU scheduler gives it a off-screen back buffer, and also gives GPU resources for the rendering pipeline and the readback manager. After that, during rendering, the off-screen back buffer chooses a slot and gives it to the GPU task queue, and then the rendering pipeline and the readback manager collects their GPU operations and encapsulate it in a GPU task. The rendering pipeline also gives the rendered images to the readback manager. So basically that's it. This is our system, and I want to show you what we achieved. Maybe I hope I can play this video. So you can see our simulator here. There are 25 cameras attached on the test car. It's running around 25 frames per second, and you can see we have 4 NVIDIA 1080 GPUs fully loaded, and our CPU is doing some serious work. I would like to show you some pictures. This is how it looks basically. I think we achieved quite real look, and in this picture you can see how we distort our images, and that's it. Thank you for your attention. If you have some questions, feel free to ask it. Thank you.
Okay, so thank you, Balázs. Time for questions.
Yeah, so we have, as you saw, we have, so we distribute the GPU operations. We have to select first on which GPU we want to which GPU we want to put the GPU operations. So, like, multiple tasks can go to multiple GPUs. I'm not sure if that's clear. We monitor, our system monitors the GPU command buffer, and we can decide if it's finished.
My question is about the rendering. How sensitive is your system to the quality of the images you generate? Because I understand you use it for training neural networks, right?
No.
No?
Actually, we don't use it for training yet.
Oh, okay.
But I think it's planned. But we use it for testing, like so the self-driving software connects to the simulator and drives like in the real world. So, but we can do fixed frame steps, and we can also do real-time running.
And I had one question as well,
Okay.
or two very short questions. One is, are you doing any compute graphics interop? And if yes, can you tell which API you're using, or is that absolutely top secret?
We don't have any compute shaders. So there are no compute parts in.
Okay. And
sorry.
the other one is, you said that you have looked at game engines, whether they are suitable for the task.
Yeah.
And I wanted to ask if you looked at Unigine, which can also be used for games, but it's an engine developed by a Russian company, and it mainly took foothold in professional use. So they are using it in airplane simulators. They also have a lot of city design software, so they can generate cities very efficiently, and with a few parameters you can tweak around and it generates an entire city for you with everything. And I was wondering if you looked at Unigine or not for this purpose.
No, we didn't. We didn't try Unigine. We used Unreal Engine.
Okay, further remarks or questions? If there is no, so let's thanks Balázs again.
Thank you.